Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 2. Today we are going to discuss lesson 11, which is combinations of capacitors. So previously in lesson 10 we have discussed what capacitors are. This is basically materials that can store charges, and when we store charges it stores some type of energy, and we can actually use that energy for various purposes. So what we actually do with those capacitors is we do not only use them individually, but we actually combine them in certain ways. So today what we are going to do is to look at different ways that we combine these capacitors to increase the amount of energy that we can actually store. So let's just have a little bit of review about capacitors and capacitance. We know that capacitor is a device that we can use to store charges. We know that if we have a capacitor, it's usually a combination of two plates separated by a distance between a dielectric material, and when we added a voltage, what happens is that some of the charges, more specifically the negative charge from one of the plate, moves onto the voltage and move onto the other side of the plate, and that's how we store charges. And we know that capacitance is basically the ability of the capacitor to store charges, and the unit that we use to talk about capacitance is in terms of coulombs per voltage or coulombs per volts, or what we call farad. That's why we use F to denote capacitance. The simplest capacitor that we know is what we call a parallel capacitor. It's basically composed of two separate plates, two identical separate plates separated by a dielectric material. And if you want to measure the capacitance of that parallel capacitor, we usually use these equations, wherein the capacitor is equals to the permittivity of the dielectric material between them multiplied by the area of one of the plate divided by the distance between the two plates. Or we can also use capacitance is equals to the dielectric constant K multiplied by the permittivity of free space multiplied by the area of one of the plate divided by the distance between the two plates. And K can be measured using this equation right here, wherein we have the permittivity of the dielectric material multiplied by or divided by the permittivity of free space. And this makes sense because if we rearrange this equation, wherein E is just equals to K multiplied by the permittivity of free space, and epsilon is just right there, so it's just the same equation. Or on the other hand, we can also use this equation right here to also solve for the dielectric constant K, wherein the magnitude of the electric field without any dielectric material divided by the magnitude of the electric field with the dielectric material. So we've discussed all of this in lesson 10. So that's how we can measure the capacitance of a capacitor. There are other types of capacitor. Aside from a parallel capacitor, you can have a spherical capacitors. And in order for you to measure that, we just have to have this equation right here, wherein the capacitance is equals to 4 pi epsilon naught multiplied by the radius of the A multiplied by the radius of the B divided by the difference between the two radius. Or we can also have a cylindrical capacitors, and we use this equation to solve for the capacitance of a cylindrical capacitors. But these are more complicated than just a parallel capacitor, and this lesson we are dealing mostly with parallel capacitors. Okay, we will have a few examples of these, but most of the time we're going to keep it simple because these parts right here are more intended for higher level of learning. But one thing that I want to note is that these examples, this parallel capacitor, this spherical capacitor, and these cylindrical capacitors are all individual capacitors, meaning they are just one. As indicated in lesson 11, what we are doing is we're actually combining multiple capacitors together. and that's what we call it combinations of capacitors. There are many ways to combine capacitors, and there are two simplest ways to do it. One is what we call a series, wherein we have and the next one is called a parallel combination. So this is one something that I want you guys to remember. Series and parallel capacitors are types of ways that we can combine multiple capacitors together. So how do we combine capacitors using series method? In a series method, the combination of capacitors is you have one, for example, right here, you have 1, 2, 3 capacitors, and then you combine them together in such a way that they are connected from one plate to another. So for example, we have this right here. Oh. So if we have this as our positive and our negative plate, it's our positive and negative plate, and that's our positive and negative plate there. So if this is our voltage, or usually we can also call this our battery, as you can see, they're in a series. They are connected side by side to each other. Wherein the positive plate of C1 is connected to the voltage, but the negative plate is connected to the positive plate of C2. And then the negative plate of C2 is connected to the positive plate of C3, and the negative plate of C3 is connected to the positive terminal of the voltage. So this is the negative terminal of the voltage, this is the positive terminal of the voltage. So this is what you call a series. They're side by side together, as opposed to a parallel capacitor wherein they sit like this, or in each capacitors are basically independently connected to the voltage via junction. So this is what we call a junction right here. And as you can see, if we have this is the positive and the negative, positive and negative, positive and negative plates, this is the negative end of your voltage, and this is the positive end of your voltage. As you can see here, the positive plate of C1 is still directly connected to the negative terminal of your voltage. The same situation is true for C2 and even C3. Okay, and as you can see here, the negative plate of C1, C2, and C3 are still directly connected to the positive terminal of your voltage. So that is the difference between these two combinations of capacitors. And these combinations of capacitors, series and parallel, has different uses. So what we are going to do is to differentiate how we measure the voltage. Basically, what we are measuring is we can measure the capacitance, voltage, and even charge Q of each of the capacitors if they are in a different type of combination. So we are going to begin our discussion with series. So what do we do if we have a capacitors in series? First, let's understand what is happening in a series capacitor. In multiple capacitors connected via series, you can think of it basically how we have discussed capacitors so far. How it stores storage is very similar to how a single capacitor or an individual capacitor would store its storage. Remember, for example, we have our voltage right here, and we know that if we have a capacitor and we added our battery or our source voltage, what happens is that the negative charges that is on this plate, what happens is they will get attracted to the positive terminal of your voltage. Remember that? We've discussed that, right? So after the negative charge has been from this plate right here, or being attracted to the negative terminal of the voltage, what happens to this plate then is becomes more positive because we are removing negative charge. And then we know that when this negative charge ended up on your negative terminal or the positive terminal of your voltage, some of the negative charges would actually will be repelled, right? Because this positive end would become a little more negative, and we know that if this becomes a little more negative, some of the negative parts will get repelled. So some of the negative parts will move from here, and they would actually go to the other plate. So if you have a single capacitor within this negative charge right here would move there. That's why we make this more negative. But if we have multiple capacitors in a series, more specifically, what happens is that this negative charge will get stored in this negative plate of however how many capacitors you have. So in this situation, you can think of this as capacitor 3 or capacitor 4. It doesn't matter. It's what happens is that this negative charge will store on this negative charge right here, right? So it will have more negative, since the negative charge is stored in this plate, it becomes more negative, as you can see there. So what happens then is, since this is more negative, what happens is basically this negative, there would be more basically there would be a transferring of negative charge. So the negative charge will get transferred here. So for example, before this happens, what happened to this whole capacitor is it becomes more positively charged. And since this whole thing is more positively charged, after this negative charge right here was attractive to this positive charge right here, what happens is that the net positive plate here would donate some of its negative charges towards the plate of your C1, and that will happen continuously across the whole multiple capacitors. So basically it's the same principle on how we discuss charges are being stored. And one interesting thing about this, if you notice, because they're basically transferring the same amount of negative charge, all the capacitors in a series have the same charge Q, meaning no matter how many capacitors you have in a series, all their charges are all equal. So the charge Q for each of the capacitors in the series are all equal. So the Q1 is equals to Q2 is equals to Qn, or however how many capacitors you have. That's one thing that I want you to already remember. All the Q, or all the charges for each of the capacitors, are equal for series. Okay, remember, for series. Moreover, if you want to measure the charge or the Q for each of the capacitor, you can use what we call an equivalent capacitor. Equivalent capacitor is basically an imaginary capacitor wherein we denote a single capacitor. This is, for example, this is your equivalent capacitor. This equivalent capacitor is basically representing all the multiple capacitors you have in the series. And to solve for Q, and that makes sense if we solve for Q for this imaginary single capacitor, which again represents the multiple capacitors in your series. If I measure the Q for this capacitor, this Q right here will then be equal to the Q of all these multiple capacitors. In order for me to measure that, I have this equation right here. 1 over the equivalent capacitor, or in this situation, 1 over the equivalent capacitance of my equivalent capacitor is equals to the voltage of my charge divided by Q is equals to 1 over the capacitance of my first capacitor plus 1 over the capacitance of my second capacitor plus 1 over however basically capacitance how many I have of my capacitor. So this is how we can measure for the equivalent capacitance, and later you would see why this is necessary, because we will use this equivalent capacitance to solve for Q, and if we manage to solve for Q, then we can actually identify now the charges for each individual capacitors, because in the end the charge for all of these multiple capacitors are equal. So let's take this and the sample problem right here. Given that C1 has a capacitance of 4 farad, C2 has a capacitance of 12 farad, and C3 has a capacitance of 6 farad, find the A, equivalent capacitance, and B, the charge of the first capacitor if the capacitors are connected in series. So as you can see here, that's your clue right here, they are in series by 9 voltage. So if I'm going to draw that, it just simply means I have something like this. So I have my voltage right here, and I have 3 capacitors. So I have my capacitor 1, capacitor 2, and capacitor 3. And I know the capacitor 1, capacitor 2, and capacitor 3 has this capacitance. So if I'm going to write my given, my capacitance 1 is equal to 4 farad, capacitance 2 is equals to 12 farad, capacitance 3 is equals to 6 farad. What it's asking me basically is, what is the equivalent capacitance? What is the capacitance equivalent? Remember, equivalent capacitance is the capacitance that basically represents all your individual capacitors. And lastly, for B, what is the charge of my first capacitor? So in order for me to solve this, I would have to understand that the formula for equivalent capacitance is equals to 1 over C EQ divided by QV divided by V over Q is equals to 1 over C1 plus 1 over C2 plus 1 over C3. Okay, and this is depending on how many capacitance you have, 1 over Cn. But in this problem, we only have 3 capacitors. So let's solve for the equivalent capacitance. We know that the equivalent capacitance is equals to 1 over C1 plus 1 over C2 plus 1 over C3, which is equals to 1 over 4 farad, not 40, 4, plus 1 over 12 farad plus 1 over 6 farad. So you can just plug that in on your calculator to measure the equivalent capacitance. But if you want to do manual, you can do so. So if you're doing manual for addition of fractions, what you have to do is first find the least common denominator. The least common denominator for 12 and 6 is basically 12. 12 divided by 4 is 3 multiplied by 1, so that's 3, plus 12 divided by 12 is 1 times 1, that's 1, plus 12 divided by 6 is 2 multiplied by 1, that is 2. So 3 plus 1 plus 2 is 6, so that's 6 over 12, so that is 1 over 0.5 farad, right? Or basically 1/2, sorry, not, so that's 1/2, or that is 0.5 farad. But that is not your CEQ. That is, this is equal to 1 over CEQ. What you're looking for is CEQ, or equivalent capacitance. So how are we going to do that? Well, if we're going to continue here, so 1 over equivalent capacitance is equals to 0.5 farad, right? So that is basically, if we rearrange this equation, this is the equivalent capacitance is equals to 1 over 0.5, or that is 1 over 1/2, which means our CEQ is actually equal to 2 farad. Okay, please do not get confused. This right here is not your equivalent capacitance yet. This is equal to 1 over equivalent capacitance, 1 over CEQ. You have to measure for CEQ. In order for you to do that, you just basically have to multiply both sides by CEQ and divide both sides by whatever your value here, and that's how you will get your CEQ. So the equivalent capacitance for this series is 2 farad. But how is that unnecessary? Where do we use this? Well, this is important if we want to find the charge of all your capacitance, which leads us to B. In order for you to measure the charge of any of these capacitors, capacitor 1, capacitor 2, or capacitor 3, you'll just have to take this equation right here, wherein we know that 1 over CEQ is equals to the voltage divided by Q, right? So if I rearrange this equation, this is basically Q is equals to the voltage multiplied by CEQ. And that's how I can measure my charge. So charge 1 is equals to the voltage. The voltage of all this series is equals to 9 voltage or 9 volts multiplied by CEQ, which is 2. So that is 2 farad. So my Q1 is actually equal to 18.0 coulombs. And why is this important? After you measure this, remember we just discussed this, for multiple capacitors in a series, all the values of Q are equal, which means Q1 is equals to 18 coulombs, which means that Q2 is equals to Q1 and Q2 is also equals to Q3, which means all these three capacitors has a charge of 18 coulombs. Okay, so if we're just looking for the first capacitor, it's 18 coulombs. If you're looking for the charge of all the capacitors, it's still 18 coulombs. So that's how you are going to measure the charges. That's how you're going to measure the charge and the equivalent capacitance in a series. But wait, we're not done yet. If we take this problem further, what if we want to measure the voltage of each individual capacitor? This is different from the voltage that your battery has. This voltage right here, 9 centimeter, is the voltage of your battery. Each of these individual capacitors would have their own individual voltage. So how are we going to measure for that? So this is the equation. What is the voltage for each of the capacitor in our sample problem 11.1? Well, we know that each of the capacitor has a charge that is equivalent to 18 coulombs. And we know that each has their specific capacitance, and the specific capacitance is given in the problem. C1 is equals to 4 farad, C2 is equals to 12 farad, and C3 is equals to 6 farad. So let me just write it here. C1 is equals to 4 farad, C2 is equals to 12 farad, and C3 is equals to 6 farad. This is given in the problem. So each of the capacitor has their own specific capacitance, and each of the charges for all the capacitors are equal, which is equal to 18 coulombs. By using this equation right here, capacitance is equals to Q over V. You may wonder, where did we get this equation? Well, remember that the unit for capacitance is coulombs per volt. Remember, coulombs per volt, and that is equals to your capacitance. Well, capacitance, which is farad is equals to coulombs per volt. So which means capacitance, which we denote by C, is basically equal to the charge divided by the volts of your capacitor. So that's where we get this equation right here. So using this equation, we can actually measure for V. What we just have to do is rearrange this equation into voltage is equals to Q divided by C, right? So the individual voltage for individual voltage for each of the capacitor is just C1 is equals to C1 over is equals to Q divided by V1, not Q1 because they all have the same value of Q. So rearranging this equation, this is basically equals to V1 is equals to Q over C1. So that's 18 coulombs divided by 4 farad. So that's 4.5 volts. So capacitor 1 has a voltage of 4.5 volts. C2 has a voltage of 1.5 volts, and capacitor 3 has a voltage of 3 volts. What is interesting, however, is if you actually add all of this, 4.5 plus 1.5, that is equals to 6 volts, plus 3, that is equals to 9 volts. And where do you notice? This 9 volts is basically the total voltage of your battery. So if we go to right here, see, this is a given. This 9 volt is the total volts of all the individual voltage of your capacitors, and that actually makes sense. Remember, if this is our capacitor and they are in a series, remember what we talk about equivalent capacitance. Equivalent capacitance is basically when we imagine these multiple capacitors in a single as a single capacitance. So this is your CEQ. And from our previous discussion in lesson 10, we know that if we have an individual capacitor, the voltage of this individual capacitor should be equal to the voltage of your battery, right? So which means that if this represents the multiple capacitors that we have, it means that the total voltage for this one should be separated into the individual capacitors, and that's what happens. The total voltage of each of these multiple capacitors is basically equal to the voltage of your battery. So I hope that makes sense. Okay, so remember, if you want to solve for the voltage of each individual capacitors in your series, you just have to use this equation right here, and you can check whether the individual voltage are correct by adding all of them, and if they all add up into the total voltage of your battery, it means that your voltage is correct. So the total voltage, so for the voltages for each of the capacitor is equal to the voltage of the battery for capacitors in the series. So this is the voltage of your battery, and these are the individual voltage for your capacitor. So that is capacitors in a series. Continuing on. This principle actually makes sense because the total sum of all the voltages for each capacitors in the series is equal to the total voltage of the battery, which is actually the reason how we were able to create the equation for equivalent capacitance. So the reason we managed to create the equation for 1 over EQ because we understand that the individual voltages of each of your capacitors in a series is equal to the voltage of your battery. So V is equals to V1 plus V2 plus V3, that however how many capacitors you have. And we know that the capacitance is equals to the charge divided by the voltage of that capacitor, and rearranging that equation we get V is equals to QC. This is how we measure for the voltage of each individual capacitors. So if we take this equation right here and we change V1 and substitute it for this value, we will get this equation. Q over C1 plus Q over C3 plus Q over C3 is equals to volts. But we know for a series that the Q are all equal. So we can actually pull out Q separately. So we remove Q, and what you see now is if we divide both sides by Q, you would get the equation for V over Q, which is equal to your 1 over equivalent capacitance. So that's how we were able to basically derive the equation for our equivalent capacitance. Okay, so I hope it's clear. So this makes sense because V over Q, as you can see here, so we know that C Q over V. So if we switch this V over Q, we just have to also switch this. So V over Q, so that's how we were able to get 1 over equivalent capacitance. So I hope that is clear. That is all about capacitors in a series. Now let's talk about capacitors in parallel. Okay, so capacitors in parallel is a little different from capacitors in a series. But how are they different? Well, first remember that for capacitors in parallel, each individual plate of all your capacitors is actually connected. One plate is connected to one side and the other is connected on the other side. So that's how we know that the capacitors in parallel, or that's how we know if the capacitors are in a parallel combination. Okay, so remember, unlike in series wherein one plate is connected to the other plate of the capacitor, for parallel, all the plates, one of the plates, more specifically the positive one, is all connected to the positive terminal. Okay, so how are they connected? Well, if you look at the wire here, so it's connected via this way. If you look at the wire here, this plate is connected via this way. If you look, however, how many capacitance you have, they are connected via this way. So that's how different parallel to series are. So some things that we want to note about capacitors in parallel. Number 1, unlike in capacitors in series, the charge Q for each of the capacitors in the parallel are not same. So if in our series, the value of Q is all similar across different capacitors, for our capacitors in parallel, our Q are all not the same. So they have their own values of Q. Another thing, you can actually treat each capacitor as if they are individually hooked up to the battery, which is very different from our series. We cannot imagine that the capacitors in our series are hooked up individually to the battery, because one side of for example, the capacitors is connected to the terminal, but the capacitors in between the two end capacitors, they're connected to each other. They're not connected directly to the battery. Unlike here, wherein capacitor 1 is connected directly to the battery, as you can see here. And this is all true for all the individual capacitors in a parallel. You can treat this as if it is connected individually to the battery. You can treat this as if it's connected individually to the battery. The same thing for your last capacitor. And it doesn't matter how many capacitors you have. But one thing here is, even if Q is not the same across these capacitors, the V is actually equal. The main reason for that is because they are individually connected to your battery. And remember from the discussion in lesson 10, the total voltage of a capacitor is determined, for an individual capacitor is determined whether what the voltage of your battery is. So if you have a single capacitor attached to your battery, this is your battery right here. If you have a single capacitor and you let this charge fully, the voltage of this capacitor would be equal to the voltage of your battery. And since we can treat all of these individually as if they're connected to the battery, therefore it tells us that each of the V, if each of the voltage for each of these capacitors are actually equal. And we can actually solve for Q of each individual capacitors using the V. So how are we going to do that? Let's look at this sample problem. Given that C1 is equals to 6 farads, C2 is equals to 3 farads, and C3 is equals to 9 farads, find the magnitude of the charge for each of the capacitors if they are hooked up in a parallel with a 8 volts battery. So this is your 8 volts battery right here, and C1, C2, and C3 are all connected in a parallel. Remember, for parallel, the Q's are not all equal among C1, C2, and C3. Q is equals to C1, C2, C3 if your parallel are in series, but they are not. But we know that the voltage for each of the individual capacitors in a parallel are equal. So how are we going to solve this? Well, we can write our given. So our given, we have C1 is equals to 6 farad, C2 is equals to 3 farad, and C3 is equals to 9 farads. And then it's asking us what is the magnitude of the charge of each of the capacitors. So what is Q1, Q2, and Q3. Okay, so what is the formula? Oh, another given to us is the voltage, which is 8 volts. Let me write this properly. So you have your C1 is equals to 6 farad, C2 is equals to 3 farad, C3 is equals to 9 farad, and you have a voltage of 8 volts. Then the formula, in order for us to solve for each of the individual Q, is just equals to C is equals to Q over V. So solution, and if we arrange this equation, this is basically Q is equals to CV. So Q1 is equals to C1 voltage. Right? So what is the voltage for each of these capacitors? Well, like I've mentioned, the voltage should all be equal. And since we can treat each individual capacitors as if they're individually connected to the battery, which means that the voltage of each of the capacitors is just equal to the voltage of the battery. So Q1 is equals to the capacitance of your Q1, which is 6 farad, multiplied by the voltage of your capacitor 1, which is equals to 8 volts. And that will give you a Q1 that is equals to 48 coulombs. And we just have to do the same thing to Q2, or to our second capacitance. The charge for our second capacitance is equals to its capacitance, which is 3 farad, multiplied by its volts, which is equal to the voltage of the battery. So 8 times 3 is equals to 24 coulombs. And for Q3, which is C3V, which is equals to 9 farad multiplied by 8 volts. And that is equals to 72 coulombs. So that is the individual charges for each of the individual capacitors. But wait, let's look even closer. Let's ask ourselves if series has an equivalent capacitor, does a parallel do capacitors in a parallel have equivalent capacitance as well? parallel combination of capacitor has a equivalent capacitance? The answer is yes, but the equation is a little different. To solve for the equivalent capacitance for a capacitor in parallel, we use this equation. The equivalent capacitance is equals to basically the sum of all the capacitance of your capacitors. So CEQ is equals to C1 plus C2 plus C3, or however how many capacitors you have. And that actually makes sense. Remember from the discussion in lesson 10, one thing that affects capacitor is area. Remember, our equation for capacitors equals to epsilon area divided by the distance between the two capacitors. Which means that the capacitor is directly proportional to the area. So if you imagine these capacitors as directly connected to your battery and treat them as if they're individual capacitors, then you can also imagine these as a whole single capacitor. But it's a little different in how you would imagine your series. In here, what is happening is basically you're taking this plate and you're combining it to this other plate, and that makes sense because this plate is connected to the positive terminal of your battery. This plate is also connected to this terminal end of your battery, and this plate is connected to this terminal end of your battery, and the same thing is true for this other plate wherein they're all connected at this end of the battery, which means you can basically take this plate and combine it to this plate. So the area of this plate plus the area of this plate plus the area of how many plates you have. In the end, what is actually happening is you're combining all of these individual plates together, and that's what happens if you're taking the equivalent capacitance is just the total capacitance of the whole parallel capacitors. And in order for us to prove this, we have an equation which we'll show later, but here's just some explanation. The positive plates are all directly connected to the positive terminal of the battery, the same thing for the negative plates. And then what we just do is we basically merge all of these plates right here into one bigger positive plates and one bigger negative plates, and that's how we get our equivalent capacitance, or our imaginary capacitor that represents all our multiple capacitor, each our individual capacitors in parallel. And the area of the plate of the capacitor increases the capacitance. We know this from our discussion in lesson 10. The capacitance is directly proportional to the area. By increasing the area, we are increasing the capacitors, and here we're basically merging all the areas. Therefore, we are just increasing the capacitance by adding all the individual capacitors. And the equation for our equivalent capacitors makes sense, because another thing that is actually true about parallel is that the total Q for each of the charge Q for the equivalent capacitor is actually also just equal to the sum of all the charges of the individual capacitors. So remember, our capacitors in parallel has different Q, but if you add all those Q, you get your Q total, and this Q total is actually just equal to the charge of your equivalent capacitor. So let's take our problem in 11.2. We know that the individual capacitance for each of our capacitors are given here, 6, 3, and 9. And we know from our discussion that the equivalent capacitance is just the sum of all the individual capacitance. So CEQ is equals to C1 plus C2 plus C3. So that is 6 plus 3 plus 9, that's 18. And if we take this equation right here, so our equations of C is equals to QV, and we want to measure our Q, that is just basically equal to Q multiplied by CV, right? And we know that the voltage for our 11.2 is 8 volts. So if we take our CEQ, multiply it with our 8 volts, we will get our Q total, or the charge of our equivalent capacitance, which is equal to 144 C. And interestingly, if you look at this 144 C, this is actually just the sum of all the individual charges that we measured in our sample problem 11.2. So our Q1 is 48 columns, our Q2 is 24 columns, and our Q3 is 72 columns. And if you add this, do not get confused now, these are the Q that we measured in our problem 11.2. We're just bringing them out now to show you that if we add all of them, it will give us our Q total, and this Q total is actually just the Q of your individual capacitance, or your equivalent capacitance, which tells us that in order for us to measure the equivalent capacitance, we just have to add all the individual capacitors of our, or in the individual capacitance of our capacitors. So therefore, so these two matches, which tells us that our equation for CEQ is correct. So let's take all of that and let's go to this sample problem, wherein we are going to add together parallel and series capacitors in parallel and capacitors in series. So let's move to right here. Okay, so let's move right here. So sample problem 11.3. Given the capacitance for each of the capacitors, so we are given the capacitance for each of the capacitors. So this the red sign tells us that that's negative, and this tells us that this is positive. The blue sign tells us it's positive. So this is our figure 3. We have 3 capacitors, and they gave us the capacitance for each of our capacitor. Okay, so if we are going to write our given, so we are, let's name this our C1, C2, and C3. So we have our C1, which is equivalent to 6 capacitor, C2, which is equivalent to 3, or not 6 capacitor, 6 farad, C2 as 3 farad, C3 as 27 farad. So what is the charge and the voltage for each of the capacitors? So what is being asked of us? It's asking us what are the charges for each our capacitors, and also what is the voltage of each of our capacitors. So how are we going to solve this? Okay, so the first thing that I want you guys to look at now is understand series and parallel combination. If you look at your C1 and C2, C1 and C2 are in what combination? If you say that they're in a parallel combination, then you are correct. Why are they in a parallel combination? Because if you look at the negative plates for each of these capacitors, the negative plates are all connected to one terminal of your voltage. So the voltage is also given. And notice that the other plates are also connected by a junction, not on the voltage, but they're connected to one of the plates of your capacitors. And this tells you that C1 and C2 are actually in a parallel combination, right? And what do we know about parallel combination? For parallel combination, that we know that the voltage are all equal. So can we say that the voltage then for our C1 and C2 is equals to 8 volts? The answer is no. Why can't we say that? Well, even though one of the or the two plates of our C1 and C2 are directly connected to our battery right here, the other end, these positive plates, are not directly connected with our voltage. If this is directly connected in this way, then the voltage for C1 and C2 would be 8. But apparently, they're connected to C3. So, we cannot immediately say that the voltage for C1 and C2 are the same, right? But what we can do now is we can create an equivalent capacitance. We can create an equivalent capacitance that can represent our C1 and C2. And if we are going to draw that, it would look something like this. Wherein this is our 27 farad, this is our C3, and this is our CEQ1. So let's write that as our CEQ1. So the question, what is the capacitance of our CEQ1? Remember, for our parallel, our CEQ is basically just the sum of all the capacitance of our capacitors, which means 6 farads plus 3 farads, which tells us that our CEQ has a capacitance of 9 farads. Right? So what do you see now? Our CEQ1 and C3 are in a series combination. And what do we know about series combination? For series combination, we know that the Q are all the same, right? And that the voltage is equals to the voltage of 1 plus the voltage of, in this situation, voltage 3 and voltage EQ1. So if I'm going to create an equivalent capacitance, or in order for me to measure all of this, what I'm going to do is I'm going to create an equivalent capacitance for my for our CEQ1 and C3, and we're gonna name that as our CEQ2, which it's gonna look something like this. So this is our CEQ2, right? So now what we are going to do, we can actually now identify the voltage of our CEQ2. And since we can imagine this is our individual capacitor, this voltage now is equal to the voltage of our battery, which is 8 volts. Okay. Moreover, we can actually also solve for our equivalent capacitance for our CEQ2. So we will have 1 over CEQ2 is equals to 1 over CEQ1 plus 1 over C3. So if we are solving that, that's 1 over CEQ2 is equals to, what is the capacitance for our CEQ1? So that's 9 farad. Plus, what is the capacitance for our C3? So that's 1 over 27 farad. And if you measure that, what is the least common denominator of 9 and 27? It's actually 27. 9, 18. Yeah, I believe it's 27. Or is it 27? Yeah, it's 27. So 27 divided by 9, that is 3. or 27 divided by 9, that's 3 times 1, so 3. 27 divided by 27 is basically 1 times 1, so that's 1. So that's 4 over 27, and that is actually equal to 4 over 27 is 1. CEQ2 is equals to 6 0 yeah 1 1 over 20, it's 0.148148. Yeah, it's 148. And remember, this is not yet your CEQ2, this is just 1 over CEQ2. So what you want to do is to measure CEQ2. This is just basically 1 over 0.148148, which tells you that CEQ2 is equals to about 6.75 farad. So the equivalent capacitance for your series is 6.75 farads. So where do we use this? We can now use this to measure for the Q. And why do we need to measure for Q? Because since for a series the Q is equal, so by measuring our Q we can measure the Q for CEQ1 and our Q for C3. So we'll take this and we'll use this equation right here, which is C is equals to Q over V. So C3 is equals to, or yeah, Q is equals to CV, or that is equals to our equivalent capacitance of 6.75 multiplied by 8 farads. So this is because this is 8 volts, and the Q is equals to actually about 54 coulombs, which tells us already that our, let's write our answers here, Q1, Q2, and Q3, and then we have our volts 1, volts 2, and volts 3. So we have our 54 coulombs. So this 54 coulombs is equals to CEQ, or the Q for EQ1 and the Q for 3, 54 coulombs and 54 coulombs. So we now have one of our answer, which is equals to 54 coulombs. Okay, and then so we have 54 coulombs for our CEQ2, which tells us that the charge for our 9 farads and our 27 farads is 54 coulombs. Now we can actually solve for the voltage of our Q, or our C3. In order for us to solve that, we just have to, so for our C3, if we take this equation Q over V and rearrange these equations to V is equals to Q over C, maybe let's move a little bit here. Okay. So we have C is equals to Q over V. If we want to measure for V, so that's just Q over C. So V3 is just equals to Q3 divided by our capacitance for C3, which is equals to 54 coulombs divided by the capacitance of 27 farads. So V3 is actually equal to about 2 volts. So we now have our answer for our V3. And next, what we're going to do is we are going to take our VEQ1 to measure the voltage for our EQ1. And why do we want to measure that? Because remember, our CEQ1 represents our C1 and C2. And since they are in a parallel, by measuring the volts of our CEQ1, this right here, it will give us the volts for our C1 and C2. So we'll just take the same approach that we did. So that's Q over EQ over V or CEQ. And we know that it's also 54 columns divided by 9 farads, which is equals to VEQ1 is actually equals to 6 volts. And this makes sense. Okay, later we will show why. So this 6 volts now tells us that the voltage for C1, or this is the voltage for C1 and C2. So we have our 6 volts and 6 volts. Now that we know the voltage for our C1 and C2, we can actually measure for their Q. So QC is equals to Q over V. So Q1 is just equals to capacitance of 1 multiplied by the voltage of 1. The capacitance of 1 is 6 farad multiplied by the voltage of C1, which is 6 volts, which tells us that Q1 is actually 36 columns. So here, that's 36 columns. And for Q2, that is just C2 multiplied by V2. So that is just 3 farad multiplied by the voltage of C2, which is, or capacitor 2, which is still equals to 6 volts. 6 times 3, that is 18 columns. So the answer is 18 columns. So now you are able to measure everything out. So this may look very confusing, but in reality it's actually not. What you just need to do in this situation here is when you have series and parallel, you have to create the equivalent capacitance for each. So here it makes more sense that you have to create the equivalent capacitance for your parallel. And by creating so, you are now creating a series, which then you have to create the equivalent capacitance for this series. And from the principle that we know, since this is a series, the Q are all the same. So by measuring the Q for our CEQ2, you measure the Q for C3 and CEQ1. And by measuring the Q for C3, you can measure the volts of C3. Now what's left is taking the volts of CEQ1, which is the same with the charge, not the volts, or the charge for C3. What you want to do then is use that Q to measure for the voltage. And why do you need to measure for the voltage? Because this CEQ1 represents both your C1 and your C2. And since they're in a parallel, by measuring the voltage, you're basically measuring already the voltage of C1 and C2. After measuring the voltage of C1 and C2, since you know their capacitance, it's now easy to measure their Q. So it's just a method of going back and forth. You're simplifying it to such that you only have one capacitors, and then you're slowly going back in such that you're revealing each of the individual information each of the capacitors has. So that is all lesson 11. I know it's a little confusing, but we're gonna spend a lot of time learning this before our monthly test, because we still have a lot of things we have to discuss. But this is the end of our lesson. If you guys have any question, please do not hesitate to message me. Thank you so much, guys, and may you guys have a great day. Mahalo.